Okay, so it's 3 p.m. now, so let's start the webinar. Good afternoon to everyone. Let me introduce myself. I'm Lee Won-Shang from KLESF University, Tunku Abdul Rahman, Utah. So 3 afternoon to everyone. Sorry. Sorry for the echo just now. Okay, I continue. Okay, today we are presenting a webinar titled Nuclear Applications Among Us. The speaker will share the knowledge with the audience on the nuclear science application that currently used for the benefit of the community. Thank you for taking time out and being here today. Just a little housekeeping before we get started. If you have any question during the webinar, please type them into the chat box. I will bring them up during the Q&A session at the end. And I will be pasting the sign-in link for attendance in a short while. So remember to sign in and sign out. Okay, so let's welcome today's speaker, Mr. Tan Chun Yuan. Mr. Tan is currently a lecturer in Department of Science and Engineering, Center for Foundation Studies, Sugarloaf Campus, Utah. So he has a strong interest in nuclear science, nuclear physics, nuclear chemistry and reactions, nuclear safety and radiation protection, nuclear reactors, quantum physics, and theoretical physics. So now, without further delay, I will pass the session to Mr. Tan. Okay, thank you. Over to you.
All right, thank you, Ms. Lee. Welcome everyone to this webinar. Sorry, I'll be a bit nervous on this because I've been a long time haven't give a webinar. Right, so allow me to off my my video and of course to share my screen. Okay, I believe you can see my screen now. All right, so it's just a simple discussion between discussion between audience and you guys regarding the nuclear application that actually among us that we don't know. All right, maybe some of us don't know, some of you guys don't know, but it does among us because the nuclear application, the first thing everyone think in mind is, of course, in my previous years, first thing come in mind is nuclear bomb. All right, but now after the past few years, it's talk about nuclear reactors. All right, so actually there's a much more application that is among us that we are not aware of. That's why we have I'm choosing this title to give to to deliver to all the audience here regarding that application that actually among us that maybe it is considered as nuclear application, just that we don't know that it is applicable in the industry. All right, so at first we talk about we talk about the introduction on the atom. All right, so every nuclear explanation will start from atom. Right, so every material we have in this world is an atom. All right, it's an atom. Consists of atoms, right? So inside our atom we have nucleus and electron. This is our basic science that everyone will know of. All right, so talk about nuclear energy. Of course, we talk about nucleus only. All right, talk about nucleus only. So the nucleus consists of neutron and proton. So actually I don't go much on the technical issue in here, so that's why I'll go a bit brief only. All right, so in terms of unstable nuclide, here, okay, instead of unstable nuclide, all right, what causes it to be unstable? All right, so unstable nuclide is caused by a different nuclear number from a stable one. If we have a stable one, then if another of his friend or his variant have more neutron or more proton, that is what we call as unstable nucleus. All right, so and this unstable nucleus we call as radioisotopes because it's unstable because radio and isotopes. All right, but last time we call it as radionuclide, but we are not calling as radionuclide anymore. We changed the new term to radioisotopes. An example of radioisotope, of course, we have helium, hydrogen. So these are the stable one. And his friend deuterium, where he has the deuterium have one more neutron more than the stable one. All right. And tritium have 2 more neutron more than hydrogen. All right. So these are the hydrogen family, but we have isotopes, but unstable isotopes. All right. So we have deuterium, we have 1 more neutron, and of course tritium, we have 2 more neutron. Of course, there are other elements also with more proton, with more neutron. All right, but that one, there's a lot of examples for it. I don't choose the example. Sorry about that. All right. So so after understanding what is unstable nuclide, we talk about the decay. All right. So what causes a decay, or what kind of half-life? Right. So after it's unstable, right? So we have a graph on it. So what is half-life? Half-life basically is the time for the amount of the radionuclide to reduce or convert to stabler nuclide. Sorry, a more stable nuclide. All right, or a more stable radioisotope. All right. So it can be converted to other form, again, more stable or less stable, depends on the situation and depends on probability. So what half-life is that if initially we start with 100% of cobalt-60 in this case, so after 1 half-life, it will reduce to 5. All right. So for cobalt-60, the half-life is 5.27 years, around this time. Right. So after that, another half-life, it will reduce by half. So another half-life, it will reduce by half until the end, until we approach to 0. All right, so this is what we call as decay half-life. So in terms of video presentation, so we can see that this one I've just prepared just for visual presentation only. So initially we have 20 polonium. All right. So now after, sorry, let me change my laser pointer. Yep. So after I play it, sorry, maybe some setting on my this thing. All right. I don't know why. All right. So after we played it, so you can see that after one half-life, around 1 half-life, we're left with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. All right. So approach to 1 half-life, it reduced by half. All right. Again, it's just a probability. The half-life is just it's just an estimation. It's not the actual value. Actually, it's all based on probability. All right. Sometimes maybe it takes maybe, let's say that half-life is 10 years, for example, and initially I have 20. So means that after 10 years, it should be reduced by 10. But each year reduced by 1, or the first 9 years reduced 1, then the last 9 years reduced by 9 is also possible. It's all based on probability. We cannot control this thing, unfortunately. All right. So the main purpose of half-life or understanding half-life is that initially we have 20. So after we pass on half-life, it will remain 10 only. All right. After pass on half-life, it will remain 10 only. All right. Again, it's all based on probability. Then another half-life, it remain 5. Then another half-life, it remain 2.5, something like that. All right. So that's the understanding of decay half-life. All right. So now, during the decay, some of the radiation will be released. All right. So most of them is, of course, can be gamma, can be here. So gamma and alpha and beta. But now we're talking about type of radiation. Of course, we have ionizing radiation and non-ionizing radiation. So most of the nuclear decay is talk about ionizing radiation. All right. So gamma is one of the ionizing radiation released by nuclear decay. X-ray, not much, but there are still probability. Although X-ray, if you have a bit of scientific background, it was released by electron. I mean the transition of electron. But there is a possibility that X-ray can be reduced from a nuclear decay, but very, very, very rare. All right, but it's considered as high ionizing also. So why does it call ionizing? Because it is it has the ability to ionize. That's why we saw ionize and material. So it can be form radical or can be very active to form with other material. All right. Whereas all these things are non-ionizing, where it has lesser energy that we are mostly used and safe to be used. All right. So after that, talk about the ionizing radiation that we are in the common ionizing radiation. So again, it depends on the situation of the nucleus. Sometimes I say sometimes I don't go to more technical. Sometimes it will release alpha ray, or that alpha consists of helium nuclide or helium isotope. All right. Or sometimes it will release beta ray. It's based on electron, but there's a lot of beta ray type. I just use one only. And of course, you have gamma ray. And of course, sometimes they will release neutron. Depends on the decay, depends on the reaction. All right. So in terms of penetration, so alpha actually cannot pass through a piece of paper, even a single piece of paper. Right? Commonly, all right, alpha particle will not pass through a single piece of paper. Right? It is very heavy compared to others. Then it is easier to interact with others. All right. So in terms of beta, again, it's just an electron. It actually can pass through papers, but it can be stopped by any metals. For this case, it's aluminum sheet. How thick is it? Is a different technical, very technical already. Right? It depends on the energy of the electron. All right. And sometimes, of course, we have gamma. So gamma depends on energy that is released. Some will pass through concrete. Some will not pass through concrete. Some will just stay inside the concrete. All right, stay inside concrete as in the energy transferred to the concrete. All right. And whereas neutron, since it is very, very neutral, and it will. Sorry. So neutron ray is very neutral. It can pass through anything. Actually, can pass through anything and can react with anything. All right. So alpha ray, very heavy, cannot pass through paper. Beta ray, is electron based, cannot pass through metal. Again, thickness of metal, certain thickness of metal. Then gamma ray basically can pass through anything, depends on the energy. All right, and neutron ray can pass through anything. All right, can pass through anything, can interact with anything, depends on him, it, whatever. All right, neutron. All right, so that is what I have in mind. All right. So of course, there are some cases that alpha can be passed through paper if it has very, very high energy. Like I said, I talk about very common case only. Common case does not pass through paper, but if we synthesize an alpha particle that can have high energy, or we create an alpha particle that can have energy, it can actually pass through anything. But of course, until now, in terms of decay alpha ray, it doesn't pass through papers. All right. And the most dangerous of these four is actually alpha. All right. Although it cannot pass through paper, if we inhale inside our body, all right, so it actually will will collide with our internal body, and it will actually damage within our body. All right. Actually, in terms of internally, alpha ray has more dangerous to us. All right. And whereas gamma is actually less dangerous. Of course, there is a possible for dangerous, but gamma is considered safer than the other two. All right. So again, this is ionizing energy, radiation. We have alpha, beta, gamma, and neutron, and it can or cannot pass through certain of the material. Depends on the energy. All right. So now we talk about the application. After understand this penetration and type of ray, go to application. So the first application I want to talk about is the neutral thing. All right, it is happened within us. We call it as radiocarbon dating. All right. So a radiocarbon or carbon-14 is actually formed in our atmosphere. All right, and it is mixed with our environment, and we somehow inhale it. It is unstable. All right, but the half-life is around 5,000 years, 5 to 6,000 years. Right, but it is safe. It is long half-life, but it is safe. It is safer. All right. So this application or radiocarbon dating is used to determine the age of certain object. So for example, if the animal is alive, so he will keep inhaling the C14, so means that it's always refreshed. Let's say that this animal maybe died dead, right, and the remain is still in the soil. So we dig up the bone, then we collect the carbon content in the bone. All right, then we go to analyze. We find how many carbon-14 is actually left inside the bone or the tissue. All right, so from there we can analyze that how many years this bone have passed through. So that's what we call it carbon dating. How much or how long does this animal have died or have dead? Then or archaeologists or archaeologists are basically, so they will use this method to discover how long does this material, wood-based, carbon-based material will have died, and how long does it die. For example, how long does this object live before us? All right, so this is an example of carbon dating, the very natural thing. All right, this one we cannot avoid. It's in our atmosphere. We really cannot avoid this one. All right. So second, of course, the known application is in terms of medical diagnostic, in terms of radiology. So like I said just now, X-ray is part of it, but again, just a few X-ray is released during decay, but mostly these are using the synthesis, or not synthesis, but electric component to produce X-ray. All right, so we have X-ray, very common, and CT scan is part of the radiology. This is transmission, where the ray will pass through you and give you just like taking a photo. I believe you understand photo. All right, just like use X-ray to take a photo only instead of using light. All right. Then of course we have another, which is actually it is in our hospital in Malaysia. It is applied in hospital in Malaysia. We call it nuclear medicine. All right. So the patient take up a mixture of radioactive tech medicine, and that patient is drink the mixture and maybe wait for some time for it to go around the body. Then the patient is put inside PET scan, all right, positron emission tomography. So from this, based on this material of this medicine, right, it is strongly absorbed by cancer cell. Mostly it's cancer cell, right? Strongly absorbed by cancer cell, all right? So if the image come with a red spot, that is where all the radioisotope is, and that is where all the cancer cell is. All right. Of course, I'm not medical doctor, but basically these are the things that I've been through. I know about. All right. So this medicine is uptake by the patient. All right. And don't think too much. It's just a normal solution. It's just a cup of water or maybe a medicine. You just drink like that. It doesn't burn. It doesn't have anything. All right. It's just a normal situation only. Also we have another one is technetium 99M. All right. So this is mostly the study of course cancer also. All right, but mostly used on bone cancer in Malaysia. All right, mostly used on bone cancer. But again, there can be a lot of cancer. Cancer in, unfortunately, we have a lot of type of cancer. Right, but these two are the most famous used nuclear medicine. All right. So hopefully these are the things that you understand. Of course, different type of imaging. One is by using PET scan, one is by using normal scan only. All right. So they absorb the light that released by the decay. Right. These things are radioisotope. They will release. They are decaying and they will release ionizing radiation. Of course, in terms of pros and cons, we use this radioisotope. Of course, we have to inhale it, then we have to suffer the the damage from it. Of course, therefore we have act on it, or we have undang on it, say that the usage must be minimum, as low as reasonable possible. All right, acceptable, reasonable, acceptable. Right. So again, why we want to use this, because it does give more pros than cons. That is the application of nuclear application. It does provide more pros than cons. Right. That's why we use it. We use as the nuclear application. All right. Then of course the same thing, we have a nuclear medicine. This one is for treatment purpose. All right. So for thyroid, the patient will take up iodine 131 to because the thyroid is absorbing mostly iodine. All right. So when we take up, the patient is given as radioactive iodine, then the iodine will be absorbed in the thyroid, and it will kill the cancer cell. All right. Of course, at the same time, the half-life must be lesser compared to, cannot be long half-life, cannot be high energy. All right. So at the same time, this one radiotherapy, I don't think Malaysia have, but we use gamma ray to target the cancer cell, directly kill the cancer cell. All right. So, but this one you have, iodine 131 we have, PET scan we have, technetium 99M we have. All right. For this one, gamma, we call it gamma knife. I'm not sure that, I'm not updated that we have this technology in Malaysia. All right, maybe have, but I'm not in my, maybe I'm not updated. All right. Now, of course, the non-medical field, we have smoke alarm. All right. Smoke alarm as in, I'm not sure that the current technology still use this alpha particle as a in the smoke alarm. All right, but there's a common usage. All right, basically, alpha particle, again, alpha particle is not dangerous if it's outside of us, but it's dangerous if it is inside of us. Right. So normally, if we put an alpha particle or alpha source here, we call it source, or decay the radioisotope that decay alpha particle, decay out the alpha particle. Then if there's no smoke here, the alpha particle can go through. So means it's good, it gives you a good current. All right. So when smoke starts to come in, then alpha particle, remember, it cannot pass through a piece of paper. It cannot pass through this thin sheet of smoke. So no signal received by the other end, then it will trigger the alarm. All right. So that's how they use the advantage of it on it. Right. So we cannot use beta, because if beta, it can pass through smoke, then no point as a smoke detector. Gamma, same thing. Neutron, same thing. So that is the advantage of using alpha particle in terms of smoke detector. So no smoke, alpha particle can go through, no alarm. Got smoke, alpha particle cannot go through, alarm will sound. Basically, it's just like that. All right. So second thing is what we call non-destructive testing. This one in Malaysia a lot, right? So of course, mostly used in actually offshore, but of course inland we also have to test whether the pipe is leaking, or the fluid pipe is leaking, or the water pipe is leaking. All right. So these are the pictures of our government. I don't know which year is this already, forgotten, right? So, but we can either use beta or use gamma to test it. I can use either beta or gamma. So for this case, we use high energy beta. All right. So to pass, if just detect like this, we use high energy beta. If it is underground, very deep underground, beta cannot pass through the deep underground. So therefore, we must use gamma, so that gamma can pass through and we can detect at the top. All right. So how to detect? Basically, if there's a water source here, we inject it from here. Then of course you'll follow the flow. If there's a leakage here, so water will come out. If water come out, means that the radioisotope or the tracer will also come out. So it means that at this spot we can detect a very high level of radiation. All right, then this spot no longer have radiation, maybe a bit, but maybe not significant anymore. All right, but we know that when it leaks out, then we can detect more radiation here. All right. Then of course, same thing as if we measured here, measured towards directly on the pipe. same thing, we measure like that, right? We don't use gamma for it. Maybe we want to check whether the thickness is still the thickness. All right. Then of course, therefore we come to thickness control. All right. So in terms of press as in compression, some of the paper, some of the metal, we want to control thickness. So some of the industry, like I said, some are not all. Some of the industry they use radiation source, and depends on the thickness. Some will use alpha, some will use beta, some will use gamma. Depends on the thickness of the material, and depends on the material they want to produce. All right. So that's how they control it. This is for QC purpose, quality control purpose, quality control purpose. All right. So if it detected, why it cannot detect on the other side, or lesser energy detect compared to others at the other side, means that that region is not the thickness that we want. So they will cut off, and of course they will reject the stock. So that is one of the application that I think very common in Malaysia also for thickness control. All right. Again, it depends on the material and depends on what thickness we want. All right. Hopefully you can able to accept. So of course sterilization also. Right. So in terms of sterilization of mostly we use in Malaysia is UV. I mean in the common household is UV because we cannot hold the radioactive source. All right. So but if you talk about big a lot of stock, right? You think of the pacifier, if there's a 1 million pacifier. All right. So of course they adjust the ray, all right, the release ray, the release energy, and they use it to sterilize all the material at once. Instead of one by one, they just thoroughly pass through everything. So that is one of the purpose of radiation in terms of sterilization. So all the product also can be used. All right, some of the household product, and of course some of them is used in food preservation. This one Malaysia we don't have. Malaysia we don't have, but maybe they did use it, not maybe, but they did use it in terms of export and import, maybe other country. All right. So in terms of, for example, let's say about fruit. All right, fruit or sweet material or a very sweet material or sweet food, it will grow bacteria throughout the time. So maybe some country they require you before export or before import, you must sterilize first. So sterilize, of course, is a food. We cannot use heat to sterilize, and there's a big stock, so we cannot use UV. So some of them will use beta, some of them will use gamma. Depends on the food type and depends on how much stock they want to sterilize. All right, and this is the symbol of food preservation where it undergoes radiation. So Malaysia, I think very less we can see this thing. That maybe there is, but very less, very less. All right. Now in terms of agriculture, also one of the application. So it's same as what we did in medical. All right. Instead of we use it to cure, we want to check how much it is uptake by the plant. All right. So this is the the application done by this researcher. All right. So firstly, they cut off. They analyze the thing first. Right. Then they let them uptake nitrogen-13, which is a radionuclide. So how much it take up, will control. Then they will study that how much take up, then how much actually absorbed by the plant. All right. Whether it's a good take up or bad take up. It can be used as fertilizer. It can use as mutation breeding. All right. Of course, this is one of the application only, not most of it. Of course, it can use as insect control also. So recall that bacterial control, if you can use previously as sterilizer bacterial control, it also can be used as insect control also. So we try to maybe sterilize the insect, for example. All right. So or we don't want that much insect within our agriculture, so we release some of the mutated insect. All right. Of course, all of them are being controlled by act, so by law, so no worry about that. All right, all of them are controlled by law. All right. So of course there are other application. So we have the neutron imaging. This is for non-destructive testing. All right. Malaysia we do have, but just that very rare to human being, very, very rare to common folks like us, right? So of course, in terms of transportation, of course, submarine. We have submarine, right? Of course, if you're old age and as me, the Back to the Future, the car also use a nuclear reactor, right? So of course, we have the usage in terms of polymers. This one is more to higher application, where you want it to cross the polymer to cross-link, or you want to cut the polymers. All right, this one more to technical already, very more to technical. All right. So of course, cannot run away is that the energy production by nuclear application. All right. So from the top until this other application, most of them is by using the advantage of decay. All right. For example, we go back. So we produce fluorine 18. We use its decay to detect. Iodine, we use its decay energy to kill cancer cell. Same thing, we use the decay of this alpha particle, this material to release alpha particle, all based on decay. Same thing here as a gamma tracer, we based on decay of a suitable radioisotope. All right. So same thing goes to here. It can be based on decay. Of course, beta can be controlled, but alpha and gamma can be is by decay. All right, it's by decay and can be controlled also somehow. All right. So medical here, some of them we use decay, and put there for a long time for it to kill to sterilize, right? And some of that can be produced. The energy can be produced. All right. So for this thing also we based on the decay, uptake of the decay. All right. So same thing, neutron imaging mostly based on the radioisotope that release neutron. And of course, in terms of transportation, most of them is not based on decay anymore. It's based on the fission reaction. All right. So radiation also we based on the decay. We use the radiation from the decay radioisotope. All right. So for energy purpose, of course, we don't use decay anymore. We use either nuclear fission or nuclear fusion. But of course, we don't have nuclear fusion yet. But there's a lot of things can be talked about energy, but I don't want to go to that. There's really a lot on it. All right. So mostly all the decay product, all the radioisotope actually mostly come from fission. All right, or we control it or we synthesize it. It is all possible. All right, depends on whether the step is correct or not only. All right, so most of the all in the world, the known data is all you are using fission reaction or breeder reactor. All right, so but the most efficient is of course the fission reactor. All right, I'm not against nuclear reaction, but I actually myself as a nuclear Ionising and nuclear student, let's say nuclear student, right? I'm not against nuclear energy actually. We are against the effect of the nuclear energy, the production. All right, but it can be controlled, all controlled by act. All right, so who are the one who control it? So first thing, of course, the International Atomic Energy Agency. This is the overall. So they control nuclear weapon, they control nuclear, everything related to nuclear, they control. All right, they have the policy, every country is based on their policy to set. All right, whereas in Malaysia, all right, so we have this government body called as under MOE, Ministry of Technology, MOT. So Atomic Energy Licensing Board. All right, and the law of Malaysia that we have, yes, we do have, like I said, we have an act of 304. All right, so every nuclear related application or nuclear related users, you must apply the license. No matter how, you must comply the license, you must apply the license. You must comply to the law and apply the license. All right, or else you're going to endanger all the common folks. All right, so whereas for the research, we have Nuclear Malaysia. All right, this is the main research. Of course, UKM, University Kebangsaan Malaysia, also have my alma mater is also providing nuclear science courses. All right, UTM, University Technology Malaysia, offering nuclear engineering courses. All right. Then, but Malaysian Nuclear Agency or Nuclear Malaysia, they are the one that do the research or they produce radioisotopes. Most of that are again government body, so they are the one that produce, and they are the one that take care of all the decay sources or unused radioactive isotope. All right. So that's believe that is my question or my presentation. So any question or anything that you want to ask regarding this? Or anyone have any question? Sorry, maybe I'm a bit nervous, but that is what I want to present. Anyone have any questions? What I want to ask?
Dear participants, if you have any question, you may just type in the chat box. I will bring to Mr. Tan. In the meantime, because of the registration there, we have some questions. So I just I paste it to Mr. Tan, okay? So
okay, sure, no problem. Oh, sorry, this is space. Okay. Okay, maybe I answer the question from the feedback form first, from the paste first. So maybe I drag to Kayla. I have two screen, I can see easily. Sorry.
Can you see?
Okay.
Not then I read out for you.
I can see. Can
Okay.
see my screen? Can see my screen, right?
Yes. See the screen, the Q&A.
Okay. The Q&A. Okay, wait for it. For a while. Let me control. Let me unshare my screen first. And share back. Okay, should be correct. If cannot, then never mind. I can see the chat box, so don't worry. So the question asked to me, the first question is, are there any new method to speed up radioactive decay? So unfortunately, radio decay or radioactive decay is based on probability, and it's based on all natural spontaneous thing. All right. There is a method to, I mean, I don't think whether it's new or it's old method, but there is a method where we can speed up the decay, but it has to study whether it's a pro decay or cons decay. For example, we can activate it. All right. So if it is, let's say. Oh, sorry. So if it's a heat, let's say it's a heat deuterium. So we want to fasten to go to hydrogen. So we can activate it with neutron. So it becomes tritium. And of course, the half-life, for example, only the half-life of tritium will be lesser than deuterium. So means that the deuterium will be much more lesser. Then we have more tritium, but since the half-life of tritium is lesser or shorter, so it will produce more hydrogen. So this is one of the method of speeding up, speeding up the radioactive decay. All right, to activate it with something else. Maybe activate by using electron, activate by using beta ray, activate by using alpha ray, activating by using gamma ray. There is a possibility, but this one have to do research whether the end result is a good end result or a bad end result. All right, hopefully I answer your question. Then number 2, how to motivate primary school people to learn and explore about this topic. This is a very, 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 very hard question to answer, because at the moment I don't have a good explanation. I mean, good suggestion for it, but maybe I don't have a good suggestion for it. But because primary student doesn't learn until this step, they don't. I don't know for sure about the current syllabus, but I don't think primary students go until this step. But the first thing first, I mean, we can target secondary school students first, right, about this topic, where of course they learn about fission, fusion, all these things, but the appropriate level should be from secondary school onwards. Primary school, I think very hard, very, very hard, unless we can produce the very good animation on it, and very, very good and very fun animation on it. That is a very hard work. A lot of work from other bodies to help us. Hopefully, I answer your question. All right. So the third question, how is it that the PET scan detect cancer cell? All right. Okay. Hopefully, my knowledge serves me correct, lah. All right. So actually fluorine 18 doesn't release gamma, it releases positron. All right. So what is a positron? Maybe I can write here. Positron is what we call as cannot do like that. Sorry, positron is beta positive, or what we call as electron positive electron. This one is very technical. All right. So when fluorine 18, when it decay, it will release a positron and something else. This one else I don't talk about that, but we talk about this one only. So when this positron react with the electron that it is within us, so these two will annihilate and release gamma. And this gamma is detected by our detector. So based on the machine and based on the engineering and based on the software, they will produce this type of image. All right. So like I said just now, the red spot is there's more gamma detected on this spot in terms of 360-degree PET CT scan actually. In terms of 360-degree, they detect that this spot has more gamma. It detects more gamma ray from this spot. So that's how they use PET or fluorine 18 and PET to detect the cancer cell. All right, hopefully. So any question else or anything? Or hopefully I answer your question. Right? So any else or any question from the floor? All right. No. The electron is actually in our body. All right. Our body have electrons. An electron came from, for example, OH minus, all those things, water. All right. These are the electrons that serve as the counteract for positron. So all these electron can be, it can be regained back, of course, because it's either we are very positive or very negative, right? It can be regained back. So the electron come from the atom or the carbon or our body. They don't come from our body. Why cancer are shown? Because let's say like that. If the human being, let's say a human being here, so every cell have an electron, have water content. All right, have a water content. So again, I try my best to explain to you only, but up to very technical, I cannot explain to you anymore. All right, hopefully, probably. So basically, if the fluorine 18 is picked up here, right? So again, surrounding this cell or surrounding this area, there is also electron. Hand also have electron. Face also have electron. Our organs also have electron. So the electron in this area contribute, and of course react with the positron, and we will release gamma. Hopefully, I answer your question. I answer your question correctly. I mean that's the way lah, but hopefully I answer your question. All right. It has to depends on where is the fluorine 18 is intake. Then next question, can you talk about nuclear effect we experience daily, good or bad, from where and how to protect nuclear effect we experience daily? Okay, this one is more to neutral, natural already. Okay. Maybe I'll go back to this question first. The cancer cell uptake this medicine. And we tag some of this medicine with fluorine 18. So let's say that this is the medicine we are talking about that the patient taking. Then this part is consists of radioactive material. This part is just a normal FDG. Hopefully, I mean that is a visual presentation of it, but not the actual one, but just a simple visual explanation. All right. So the medicine itself is tagged with radioisotope. That's why the medicine also that type of cancer cell will absorb this medicine. That type of cancer cell. All right. Hopefully I answer your question. All right. So the question, can you talk about the nuclear effect we experience daily and good or bad, or from where? Like I said, go to neutral, neutral blood, natural. Okay. So like C14 is around us. We cannot run away. All right. The soil, like the soil, if depends, if naturally, like talk about naturally, we have also radioactive material. We have 238 uranium, not much but small content. We have what else? Mostly nuclear. Of course, we have cobalt inside, we have ferrum inside. Some of them are actually have the family have family have radioisotope inside our soil, but it's commonly distributed among the soil. All right. So these are what we call as a normal norm. Norm. So normal, natural occurring radioactive material. These are the one that we cannot remove. It is within us. It is in our environment, and it does not actually give us a bad effect. I don't know why, but maybe we already used to it. We already mutated and against it. All right, it is within our surrounding. Even a simple wall, maybe there is a radioactive material, but very few, very few. All right, that's why it's not. Right, natural occurring radioactive material. Of course, the most example I believe you heard our ministers talk about is that the banana. All right, banana, of course, there's a lot of potassium. Right, a lot of potassium. So in terms of abundancy, there is K40 inside. All right, very small percentage, very small percentage, very small percentage, but it doesn't affect our body. Same like if you eat too much of banana, you get sick, but not sick of K40, potassium 40. All right, you're sick of because you have too much of the mineral from the banana. All right, so but K40 will not directly affect us in terms of our body, in terms of banana. All right, I hope I answer your question. So unfortunately we cannot avoid from nature only. We cannot avoid from nature. This one cannot, unless for example me, I create something very radioactive, then I dump it somewhere. Then one is very wrong of me. They're very wrong of me. So that area will be very radioactive. Fortunately, our ALB just now, they have set a few towers around Malaysia that they can detect radioactive. If you still recall that during Japan Fukushima Daiichi accident, the reactor explode, they do detect the radioactive material that flow to Malaysia through air. They can detect from that. All right. So we cannot feel the difference between whether we have radiation on us or not. We really cannot feel it. Just like you do an X-ray, just like that. All right, but X-ray must be sharp, must be short. But if you have long exposure on something, radiation, of course, it will have very bad effect in our body. All right. So I think that's it. Right. Okay. Then we go back to the question. Our friend here asked, if we can tag the cancer cell, then we can target the cancer cell and kill them. We must have the correct energy. And in terms of cancer cell or killing cancer cell, it is very risky in terms of using, if we don't do a proper research. If it is uptake by the cancer cell and the energy also damage the cell around the cancer cell, the healthy cell around the cancer cell, then that is also a bad effect. All right, so we don't want that. So that's why in terms of nuclear application, we want to find the middle point. It does help in terms of diagnostic, or does help in terms of positive effect, but not too much of negative effect. Not too much of negative effect. I hope I answered your question. I think this is a normal question. Actually, this is a normal question by all participants or all audience that listen to this type of topic. All right. So we have a question here. I read in news that Peru has granted mining of thermite. How does it affect? Actually, Laterite, one of the unstable nuclide or unstable nuclide it go back to here, go back to this one. Right, again, it's my point of view only on this one. Again, if what does the government did or what does the agency did, I'm not representing them. All right. So if the radioactive material is scattered among the floor, it's actually not that dangerous. If it is take up, if we dig this up and we refine a pure radioactive material, then this is dangerous. Right? If you refine with centrifuges, you get the pure radioactive material. That is dangerous. All right. Then how to handle this thing is we have to follow the law. I mean, the law states like that. All right. So we have to follow the law. So normally it will keep in nuclear Malaysia or nuclear Malaysia authorized places where it is must be very far from common folks. This is a law. It states like that. It must be very far from common folks, and of course they must follow. That's it. All right. If you talk about, you can talk about liners, but that one is out of my reach. That is what's called safety protection, nuclear safety. Right. So we want to take care of our surrounding. We must ensure that the surrounding doesn't affect by nuclear radiation or nuclear effect. All right. Last time as in many 10, 15 years, 50, 60 years ago, we don't have the act. So we don't do this type of thing. I mean, all the country don't do this type of thing. But now we have the act, we have the knowledge already, so we can handle the waste properly, because radioactive waste properly. Hope I answered your question. Right? Theoretically, it should not harm the surrounding. Theoretically. And for the law, it should not harm the surrounding. Any else? Or anyone have any question else? Oh, sorry. Oh, what happened here? Oh, sorry for that. All right. So again, I try my best to explain it. Okay, I'm not very, because those are very specific field to answer. Those are very specific field to answer. Letanite, again, that is a rare earth material. So rare earth material is now applicable to all our devices. All right, it can be, mostly devices, very small part, and of course it can be. I cannot tell you much more, but I know it's devices only. And of course it can be applied in other field, proper, because it's rare earth, so it has a very special properties that I don't know of. All right, it's not my field in terms of rare earth. All right. So if there's no question else, hopefully I answered the question. If I have any wrong information given to you, that is purely me lah. But that is what I've known, or I've known of. All right. So now there are simple quiz for you guys, maybe to win the KLESF limited T-shirt. So a very simple question only, but we only choose the top three winners, or top 4 winners, depends on how Miss Lee want to arrange it. You can either scan the QR code, or you can join this, or let me copy the link and put it in the chat box. All right, you can answer the question, very easy, 8 question only, very easy. All right, so the quiz is open until 25th of August, 4 p.m. All right, so I recommend you guys to use your email as a username so that we can trace you back. All right, because this is not related to Zoom. This quiz is not related to Zoom, so we cannot trace back if you use your name only. All right, so I think my speech is until here. My webinar is until here. If there's no more question, then I'll pass back to Miss Lee.
Okay. Thank you, Mr. Tan, for this very insightful webinar. I hope if we miss out your questions, so just in case we miss out, so you may paste it again at the chat box. So I hope we answer of the question. And for those who are watching from YouTube, I also pasted the quiz link, so you may join the quiz. And I have a small request. I would like to request those you are able to turn on your camera, let us take a group photo. So if you're unable to turn on your camera, maybe you just give a thumbs up reaction. Okay, so one moment. Okay. We wait for a while if anyone can turn on your camera. Okay, so okay, never mind. Then I just take a few screenshots.
Hello.
Oh yeah, I saw Wong just now. And Wong have a request. So Mr. Tan, do you mind to share your slide?
Sure, no problem, no problem. I can let me clean all the writing first.
Okay, sure. Once I get a PDF file, that I will share to you.
Yeah, sure.
Okay. Okay, so I have seen Liu also turn on the camera. Okay, so get ready. I will take a few screenshots. Okay, 1, 2, 3, smile. Okay, done. Okay, so hope you all will join the quiz. So we will choose the top 3 winners. Then once we have the winner, I will contact them to redeem the prize. Okay, then let me paste again the sign in, sign out form link. Kindly sign out and help us to fill up the feedback form. So I would like to promote tomorrow at the same time, 3 p.m. Malaysia time, we have another webinar. Title is Immersive Technology for Medical Science. So if you are free and able to join us, so hope you can join us again. If you want to know more detail about the webinar, you may get the links and the description from KLESF Facebook. Okay, so before we end the webinar, is anyone have any question? So, okay, no, just in case if you want to ask any question to Mr. Tan, you also may email or contact KLESF. Then we will pass the question to him. Yeah, this is the webinar tomorrow, Immersive Technology for Medical Science. The webinar will be presented by our Utah's undergraduate student. They're working on a project. So for this time, we have an opportunity for them to show and explain more about their project. Okay, so it's about time now. So that's all for today. Thank you, everyone.
Thank you, everyone.
Okay. Once again, thank you, Mr. Tan.
No problem, no problem.
Okay, so thank you. So we will end the webinar.